Welcome back to Hypothesis Testing. Done right, part 3 of 14. In part 2, we built the idealized test statistic, estimate minus null, over the standard error, but it contains sigma, the true population standard deviation, which nobody ever knows. Now we fixed that, and the fix gives us the t-statistic you will actually compute, with heavier tails that gracefully thin back to the normal. The idealized statistic contains sigma, the true population standard deviation of daily returns. Sam does not know it. Nobody ever does. We can only estimate it from the same sample, using the sample standard deviation s, the square root of 1 over n minus 1, times the sum of squared deviations from the mean. The divisor is n minus 1, not n, the Bessel correction from chapter 1.3, which makes s squared an unbiased estimator of sigma squared. We spent 1 degree of freedom estimating x bar, so only n minus 1 pieces of independent information about spread remain. Replacing the unknown sigma with the estimated s gives the statistic we actually compute, the t-statistic, x bar minus mu naught, all over s divided by root n, where mu naught is the null value, here 0. The quantity s over root n is the estimated standard error. But swapping c for sigma is not free. We have replaced a fixed constant with a random quantity. S jiggles from sample to sample just as x bar does, and dividing by something random adds extra uncertainty, fattening the tails. William Gossett worked out the exact consequence in 1908, publishing under the pen name Student, because his employer, the Guinness Brewery, forbade staff publications. The result, when the underlying data are normal, the statistic t does not follow a standard normal. It follows students' t distribution with n minus 1 degrees of freedom. The t distribution is shaped like the normal, symmetric, bell-like, centered at 0, but with heavier tails that account for the extra uncertainty in s. The fewer the degrees of freedom, the fatter the tails. With 4 degrees of freedom, they are noticeably heavy. With 30, the t is already almost indistinguishable from the normal. And here is the clean bridge back to chapter 1.4. As n grows, s converges in probability to sigma, so the random denominator stops being random, and the t converges to the standard normal, the CLT promised. 1 point of rigor: the exact t result requires the underlying data to be normal. Real returns are fat-tailed and skewed. We still use the t because, by the CLT, the numerator x bar is approximately normal for large n, so the whole statistic is approximately t. With 252 days, the approximation is excellent. With 8 fat-tailed returns, neither the exact nor the approximate result is trustworthy. To summarize part 3, because we never know the true standard deviation sigma, we estimate it with the sample standard deviation s, and that swap gives the t-statistic distributed as students' t with n minus 1 degrees of freedom. Its tails are heavier than the normals to pay for the uncertainty in estimating s, and they thin back to the normal as the sample grows, which is why for large samples, people use the words t-statistic and z-statistic almost interchangeably. The exact t distribution needs normal data, but for large samples, the central limit theorem rescues us, making the statistic approximately t even when returns are fat-tailed. In part 4, we put real numbers in, compute Sam's t, and see the standard error deliver its single most important practical lesson.